Thank you very much for the introduction, Evelyn. And first of all, I want to thank the organizers for inviting me or drafting me to give this series of lectures. I think, so let me tell you what was the order. Okay, the order was give 3 lectures on an introduction to Euler and Navier-Stokes equations, and specifically well-posedness for smooth solutions, local in time, of course, global well-posedness of weak solutions, Leray-Hopf solutions for Navier-Stokes, uniqueness criteria, Prodi-Serrin theorem, some weak solutions for Euler equations, and whatever else I might like. Okay, so that's what we're going to do in the next, in these 3 lectures, hopefully. Okay. Disclaimer, so first of all, I am not really assuming much as far as fluids background, but I have to assume a lot of analysis background. Okay, so I will try to, whenever it's really needed, I will try to specify all the different spaces and exponents, critical exponents, etc., as we go along. Okay, now let me start really nice and easy. Okay, so we'll assume we have a fluid which occupies some domain in Rn, some omega in Rn, and here is going to be 2 or 3. Okay, those are the ones that we're most interested in. I'm not going to be concerned with Navier-Stokes or Euler in dimensions other than 2 or 3. Okay, so omega is the fluid domain. Okay, and okay, so there are 2 main descriptions possible for fluid flow. Okay, so 2 descriptions. Eulerian and Lagrangian. Okay. So what I'm doing here is actually reminding you that the Euler and Navier-Stokes equations are not just PDE, but they mean something physically. They are a model of something. Okay? All right. So in the Eulerian description, you have my domain omega, where the fluid lives, and at each point, at each position x and time t, I have hydrodynamic quantities. Yeah. This is an I. U at time t position x, okay, P, which is the pressure, it's a scalar, okay, and density. Also a scalar. Okay, so I look at these hydrodynamic quantities. So I have a little arrow, and in the Eulerian description there is an implicit assumption, which is that the fluid is a continuum. So that at every point x and time t, I have one of these little arrows, which is the flow. Okay. Now, okay, so the pressure P gives rise to the pressure force minus grad P. This is greater than x. Okay? And this is the force acting on fluid particle due to outside or other fluid particles. In a sort of a normal direction. I'm going to leave it at that. I don't have time to get into this, but there's more to it. Okay? The question is, why the minus sign? Okay. Because the flow moves from high pressure to low pressure. So in the direction opposite to the gradient. Okay? Okay. Units or dimensions. These are important. You have L, which is the unit of length. T, unit of time. And M, unit of mass. Okay, so how do the equations come about? So first of all, this is the Eulerian description. In the Lagrangian description, which we will meet, okay. In the Lagrangian description, I describe the fluid flows. So eventually I'm going to find it PD for you, P and rho, okay? But before I get into that, let me tell you what is the Lagrangian description. So the Lagrangian description, we look at the trajectories of a given fluid particle. So I paint a little fluid particle A, I paint it red, and I follow it in time. Okay, so if I follow it, it moves with the flow, and at time 0, it's at position A. Okay? Okay, so the flow is incompressible. What that means is that the amount of fluid inside a given fluid domain, if the fluid domain is moving with the flow, the amount of fluid doesn't change. Okay, the total mass of the fluid, the volume doesn't change. So what is the volume? The volume is the integral of x of t and d. So x of t and d represents the domain which started out, so the particle started out in d, in some subdomain d in omega, and they move at time t, they're at wherever the flow took d. Okay, so I'm thinking of some little portion of fluid inside my domain omega, and I track where this goes with the flow. Okay, that's called a material domain. Okay, so the volume doesn't change, which means you have this. Okay. Okay, so like I said, x of t in d is x of t in A, such that A belongs to D. Okay? Now, there's something called the transport theorem. Which I'm not even going to state as a theorem, actually, which says that for any function f of t and x, then I take the time derivative of f, of the integral of f in a material domain, and this is equal to f sub t plus the divergence of uf in the same domain. Okay? Okay, so if f is equal to 1, then this is 0, and this is just the divergence of u. Okay? So the flow will be incompressible if for any subdomain D, ddt of the integral of divergence of u on x of t and d is 0. Okay, so flow is incompressible if and only if ddt, the integral of divergence of u is 0 for every d. Okay. And that's basically if and only if the divergence of u is 0. This if and only if, of course, is assuming subject to regularity conditions of u, but let's forget about that. This is heuristics at this point. So everybody's smooth. Okay? So divergence of u equals 0 represents incompressibility. That's the point. Okay? All right. Okay. So math models of incompressible flow. Okay? Okay, so first of all, you have conservation. So these comes from just the basic laws of physics. So you have conservation of mass. ddt of this is 0. So this is the density. Okay? And you look at the density on a domain which travels with the flow. That has to be 0. And ultimately, if everybody is smooth, that comes down, because of the transport theorem, that comes down to this. Okay? And then you have conservation of momentum or balance. Momentum, i.e. Newton's second law. Okay. Okay, so this comes down to mass times acceleration equals this. Okay, what is this? So first of all, this is the acceleration of a fluid particle. This is equal to, so if dx dt is u of t and x, when you take a time derivative of this, d squared x dt squared, you're going to get the partial derivative of u with respect to t plus the gradient of u times dx dt, which is u again. Okay, so what this is d squared dt squared of x for a given fluid particle A. Okay, this is just mass times acceleration. Okay, so what is this? This is the force per volume, per unit volume, acting on a fluid particle, if you want. Okay, this is the force normal. So the idea is you're going to take a little particle, a bunch of little particles of fluids. You're going to do this with some infinitesimal little d, and then this is the force acting across the boundary of your material domain, okay, in the direction normal to the material domain. And this is a shear force, okay. So this is the friction. This is due to friction with the other particles, okay. So this is a shear force per volume, per unit volume, and this is a normal force per volume. This is the pressure force, and this is the friction force. And this parameter nu, okay, which can be non-dimensionalized, okay. In other words, we can get rid of all of these units, okay. This is the kinematic viscosity, or mathematical viscosity. It's 1 over Reynolds number, and it's called okay. So here they are, Euler and Navier-Stokes equations. This is for a non-homogeneous fluid, and we are going to assume throughout that rho is constant. And being mathematicians, we're just going to assume that rho is 1. Rho constant is a solution of this equation for any u, okay? And since divergence of u is 0, and it's a reasonable assumption that my fluid has constant density, okay? Okay, so if the density is equal to 1, then finally I land at the Euler and Navier-Stokes equations, except that now we know what each one of these terms means. So here is our PDE. Okay, I need to explain better what this term means because u is a vector, so this doesn't a priori make grammatical sense. So what is u dot grad u? It's the formal differential operator u dot grad applied to u. So this is the differential operator ui d dxi, sum in I, and it's going to be applied to each one of the components of u. Okay? All right, this is exactly what you get when you differentiate dxet again with respect to time. You get exactly that. Okay? So this system of equations with n plus 1 unknowns, okay, and n plus 1 equations, okay, this is the Euler and Navier-Stokes equations. When u is equal to 0, these are the Euler equations, and they correspond to ignoring shear effects, ignoring friction between particles, okay? And u positive are the Navier-Stokes equations. Okay? Okay. Okay. Before I begin actual analysis for this PDE, there's one more object that I would like to introduce to you, which is really important in incompressible flow, which is the vorticity. So the vorticity is defined as the curl. It's a vector, and it's defined as the curl of the velocity vector. And what it is a measure of infinitesimal rotation. Okay. Because of the divergence-free condition, incompressible flows tend to rotate. There's a tendency to create what we call an eddy. Okay, so vorticity is a very important quantity in compressible flows. It tells you it's very descriptive of what the flow is doing. And one of the key facts about vorticity is that it has its own evolution equation. Okay. So this is the curl, right? Or rot. Okay? Okay, so this is the vorticity equation, and the way you get it is you just take the curl of the velocity equations, the equations for velocity. If you take the curl, you get d omega dt, and then you get the curl of u dot grad u. Okay, so the curl of u dot grad u is equal to u grad omega minus omega grad u. And again, when I write this, what I mean is the differential operator u dot grad applied to each of the components of omega, and here is the differential operator omega dot grad applied to each of the components of u. Okay? Okay. I want to introduce some notation, and now we're going to get serious. I'm going to use H, in fact, HM is a Sobolev space with m derivatives in L2, okay, m derivatives in L2, and HM sigma means W2M divergence free, div free. Okay. Remember, we're going to be doing this in all of space. Of course, we can work on Euler and Navier-Stokes equations in bounded domains, in periodic domains, in domains which are bounded in one direction and not bounded in another direction, and that's a whole nother ball game, which I will not be discussing. Okay? So, let's talk about the first question for a PDEist is well-posedness. Okay, let me give you smooth initial data. Okay, I don't have boundary data because my boundary is at infinity, but let me give you smooth initial data, and let's try to find a smooth solution. Okay? Okay, so I'm going to start explaining the following theorem. Fairly old theorem due to a bunch of people, so I'll just okay. So here I'm going to have nu greater than or equal to 0, so I'll do Euler and Navier-Stokes at the same time because it's really the same proof, or almost the same proof. Okay? Okay, so let u naught be in HM. Do I want R3? Yeah. Okay. HM sigma of R3. Okay? Then there exists a time t star depending on u naught HM and on nu, okay, such that there exists a unique u, which is going to be, oh God, L infinity in T and HM in X. So let me explain what I mean by this. First of all, the HM spaces are HM of R3, okay? The time spaces, when I write this and I write a time t star, it means from 0 until t for some t less than t star, for any t less than t star. So in other words, this is always local in time. Okay, what I'm writing here is local. I don't have enough space to write L infinity loc t. That would be a little cumbersome here. And Lipschitz continuous in time into h m minus 2. Okay, so it's going to be in here. There exists a unique such u, okay, and it's also continuous in time into, I want HM, yes, weak. So what does this mean? This means HM with the weak topology. So if m equals 0, it would be L2 with the weak topology, which is different than a weak L2. Okay? Weak L2 is L2 infinity. It's another space. We have a problem with too many spaces. I'm sorry?
Probably have a condition on M in this theorem.
Yes, I do. I'm not done. Where M is bigger than 3/2 plus 2. Okay? Since I'm doing Euler and Navier-Stokes at the same time, it's 3/2 plus 2. If I was doing just Euler, I'd have 3/2 plus 1. Okay. But I want to do it at the same time. Okay, we're going to be using this theorem for very smooth initial data, so who cares? Okay, so I'm going to be describing the main steps in the proof. Okay. I don't have time to do everything in absolute detail, but I want to give you a very good idea of what's involved. Okay, so first of all, I'm going to split this in step 0. Okay, is introduce an epsilon PDE or an approximate PDE. Okay, I'm going to be setting this parameter epsilon to 0. I will introduce an approximate PDE, and which approximate PDE is crucial here. Okay, so epsilon PDE, and I will show that it satisfies Picard's theorem. Okay, what do I mean by this? So I'm going to introduce an approximate PDE, okay, and it's going to be looking at something like ddt of my approximation u epsilon equals to a right-hand side, okay, which is a function of u epsilon. Okay. Of course, this is in infinite dimensions, it's in a Banach space, but I'm going to be, my main tool is going to be Picard's theorem for ODEs in Banach spaces. All right, step 1 then is to show that there exists a solution until some time t epsilon. Okay. Positive. Step 2, this is for the epsilon PD, for the approximate PD. Step 2, t epsilon is infinite. What I mean by this is I will show, the step 2 is to show that the solution to the approximate PDE exists globally in time. Okay. Step 3, uniform estimates for the solution. So what kind of estimates do we have for u epsilon which are uniform with respect to the parameter epsilon? Okay. Until some t star. That's when t star will appear. Step 4, u epsilon is going to be Cauchy, or actually compact in L infinity hm minus 1, I think. Yeah. U epsilon will be compact in L infinity, in fact in C0, hm minus 1. Okay. And it has a limit. Okay, so this is compact, so it has a sub-sequence. I'll think of epsilon as some sequence. Okay, I'm abusing notation here. Family, subfamily, whatever. Okay, and then there's I can pass to a subsequence which converges in this topology to some limit u, which belongs to continuous to hm minus 1. Okay? All right. I'm going to be writing u epsilon converges to u by passing to whatever subsequence I need as necessary, okay, without relabeling. I don't want to worry about relabeling. Okay? Okay. Now, because of the uniform estimates, these will be inherited by u. Okay, so I have a compactness, and I'll have u belongs to L infinity hm, and lip, this is in time, this is in x, lip into hm minus 2. Okay, lip in time. Okay. Step 5, u solves PDE and is unique. Okay, step 5. All right, so let's go for this. Okay, so step 0. The epsilon PDE that we will look at is dt v plus, let's see. All right, so first of all, okay, j epsilon v dot grad j epsilon v, and then I take j epsilon of that equal minus j epsilon grad p, let me write q here, q plus nu j epsilon Laplacian j epsilon v, and v at t equals 0 is j epsilon 0. This is not really needed. Okay. All right. So what is j epsilon? What does this mean? Okay, what's j epsilon v? So we start with a Friedrichs modifier. Which is just a function of one real variable, which is values between, say, 0 and 1, which has support in the unit ball, whose integral is 1, the standard modifier. And we look at eta epsilon, which is just 1 over epsilon, in this case cubed, eta of norm x over epsilon. Okay, and then j epsilon f is just a convolution with this modifier. So what do we do here? So what's my epsilon PD? I'm looking for a function v such that the time derivative of v plus the convolution with the modifier eta epsilon of the convolution with v dot grad convolution with v is minus convolution grad q plus nu convolution Laplacian convolution v. Okay, solution of epsilon is, I will write u epsilon. So this is epsilon. Okay? So I'm going to write u epsilon to be the solution of this epsilon PD. Okay, so I didn't want to write it here, because there would be too many epsilons. Okay, so the next thing that I need to use is an operator called P, called the Leray projector. Okay, the Leray projector will take LP of R3 to LP of R3 continuously, and what it does is it throws away the gradient part of a vector field. Okay, so again, when I write LP of R3, I'm thinking of LP of R3 cubed, a vector field. Okay, so I take F and I write f as the gradient of some q plus something which is left over, which is going to be divergence free. Okay, h divergence free, and this p of f is h divergence of h is 0. When you have boundaries, it's a little more complicated, but we, thank goodness, do not have any boundaries. Okay. Okay. So I'm going to apply this Leray projector P to my epsilon equation, and note that, oh, I forgot one very important thing. I need divergence of v equals 0. Okay. So I want v to equal to pv, okay, so because v is already divergence free. Okay. So when I apply p, what I get is epsilon. So this is p epsilon is dt, and now I can write u epsilon, which is going to be my solution, hopefully. So it's going to be dt u epsilon plus p j epsilon u epsilon dot grad j epsilon u epsilon is minus. So that does away with the pressure. The pressure is already a gradient. Minus j epsilon commutes with the gradient. So there. So this is going to be nu p j epsilon Laplacian j epsilon u epsilon. Okay? And u epsilon equals to p. U epsilon encompasses a divergence-free condition, and of course, u epsilon at t equals 0, which is equal to j epsilon u epsilon naught. So now I have p of this. And what we do is we're going to find a solution to p epsilon and then say, okay, this is so the equation for u epsilon is this plus a gradient, and that gradient is my minus grad q epsilon. Okay. So what I'm going to do now is to put this term on my right-hand side, like so, and I will call this f of u epsilon. Okay. So what I'm looking for ultimately so I have an equation which reads dt u epsilon equals to f of u epsilon, and I want it to be, I want a solution inside hm sigma. Okay, so okay, so at this point what we need to do is use Picard's theorem in Banach spaces, which basically comes down to getting a fixed point for the integral in time, blah, 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 of f of u epsilon, f of u. Okay, so the ingredients for Picard's theorem are tool. I will view this as an ODE in hm sigma, and I want to use Picard's theorem for ODEs in hm sigma. Okay, so what I need is that f takes hm sigma to itself, and that f is Lipschitz in hm sigma, i.e., I need to compute f of u minus f of V in HM, and I need this to be bounded by some constant mu minus V. Okay. Okay. So let's verify that F takes HM sigma into HM sigma. Let's get our hands dirty here. Okay. So one, I'm going to estimate F of U H M. Okay. I don't need to verify that the divergence of F of U is 0. In other words, I don't need to verify that once I know that it's at HM, I don't need to verify that it still is divergence free because F has a Leray projector in front of everything. Okay? Therefore, that part is easy. The fact that the sigma part is easy. Okay? All right, so all I need to verify is that I can bound this in terms of HM norms of U, okay, because those are going to be finite, and so that's what I need. Okay, okay, so this is going to be the HM norm of P, or minus P. Let's see. I have J epsilon U grad J epsilon U plus nu J epsilon Laplace P Laplacian J epsilon. Okay, this is what I want. And I need to estimate this. All right, this is the easy term. Okay, this is two derivatives of some J epsilon of J epsilon. When I take two derivatives, okay, I can throw these derivatives on U. Not a good idea because I want this in HM. So I will throw the derivatives onto my convolution, my modified term. Okay, and when you differentiate twice, you get a 1 over epsilon squared. Okay, so this term here, the HM norm, is going to be bounded by nu over epsilon squared times J epsilon U HM. Yeah. Okay. Okay. Which of course is bounded. Once I know that this guy belongs to HM, the convolution keeps it there. So this is the easy term. Okay. Actually, I'm using the triangle inequality here. And this term here will continue here. Okay, so I want to bound the HM norm of P of J epsilon U grad J epsilon U in terms of UHM norms. All right, so here we're going to use a trick, which is that U, which is that V dot grad V, when V is divergence free, can be rewritten as divergence of V tensor V. Okay. So what does this mean? Okay, so first of all, as we know, V dot grad V actually means the differential operator V dot grad applied to V, so you get a vector. Okay? Talking about grammar here. V tensor V is a matrix, and this divergence of this matrix means a divergence row by row. So I take each row and I calculate the divergence. That gives me a scalar. Okay, so this gives me a vector, so this makes grammatical sense. Okay? And this is just an easy calculation to show that this is true coming from the divergence-free condition. All right, so then if I use this here, then what do I get? First of all, P of HM, and without the P is the same thing. So this is the same thing as divergence, if you want J epsilon, divergence of J epsilon U tensor J epsilon U. Okay. Now I'm going to commute these. This is divergence of J epsilon tensor J epsilon U. Okay, and then again, I'm going to put this guy here in HM. So when I take the divergence, I will put the derivative onto my mollifier, and I have to pay a price of getting a 1 over epsilon. Now, the condition on M, which he so correctly pointed out, is so that HM is an algebra. Okay? Therefore, this product here can be measured by J epsilon U HM squared, and J epsilon preserves HM, so this is simply bounded by constant over epsilon U HM squared. Okay? So there. So this term here is going to be bounded ultimately by a constant over epsilon UHM squared. Okay, this shows that F takes HM into HM. So if U is at HM, F of U is also in HM. Okay, very good. Okay, where was I? Yes, so that's the proof of 1. The proof of 2. Proof of 2 is quite similar. There's no real new idea. I will just write F of U minus F of V in HM. So this is going to be, this is F of U minus F of V, and this is quadratic with respect to U and V. Okay, so I can write, so this term here is linear. So I can write this, let me start with the Laplacian term because that's easier. I'm just going to get nu times P J epsilon Laplacian J epsilon U minus V HM, and that's going to be bounded by constant over epsilon squared U minus V in HM, plus we just add and subtract the right thing. Minus P J epsilon U dot grad J epsilon U plus P J epsilon V dot grad J epsilon V. I need more space. Okay, the first one gives automatically constant over epsilon squared U minus V HM. Okay. And this term here, because it's quadratic, you can add and subtract minus J epsilon V dot grad J epsilon U plus J epsilon V dot grad J epsilon U, and you wind up with, throw away the P, let me continue here, otherwise you won't be able to see anything. Oops. So I'm going to get J epsilon of u minus v times J dot grad J epsilon u plus J epsilon v dot grad and this, you again use the tensor product idea, and you wind up with constant over epsilon. This term will give you u minus v in hm times u in hm. This will give you u minus v in hm times v in hm. So you finally have u in hm plus v hm times u minus v hm. Lipschitz, not uniformly in hm, but it's locally Lipschitz, and that's all you need for Picard's theorem. Okay, so here we're going to get this plus constant over epsilon okay. We're done with that, and therefore, step 0 was introduce the epsilon PD. Step 1 was to show that it solves, that it satisfies Picard's theorem, and therefore we have existence and uniqueness locally in time of a solution, a C1 solution in time. Okay, all right. So by Picard's theorem, there is a sometime T epsilon positive such that there exists a unique U epsilon, okay, which is going to be actually C1 in time into HM. Starts out being C0, but then you exhibit it, you construct it as an integral in time, so it ends up being C1. Okay, so 2. Show that T epsilon is infinite. So T epsilon equals plus infinity. Recall, epsilon is still fixed. We're still doing the epsilon PD, so epsilon is fixed. I do not have to worry about epsilon going to 0. Okay? Okay, so here what we need to do is to use the continuation principle. So as long as you remain in HM, you're fine. You exist for a little bit longer. Okay? So the only way to stop existing is if you leave HM, so the HM norm has to blow up. So it's enough to show that we have a uniform bound on the HM norm, okay, for a fixed epsilon. Okay. To show the bound can depend on epsilon, that's not a problem. Okay, so what do? So I want to estimate the HM norm, so I'm going to differentiate my PDE, and I might as well do it using Leray projector, because I don't want to have to deal with the pressure. Okay. So I've got dt u epsilon plus p times j epsilon u epsilon dot grad j epsilon u epsilon equals to nu times J epsilon Laplacian, J epsilon U epsilon, and I forgot a P here. Okay, so I'll take the alpha derivative in x, and I get dt d alpha U epsilon. Well, never mind. Okay. So I'll take the derivative of this, and then I'll multiply this, take the inner product with d alpha U epsilon, and integrate. Okay, in space. Integrate the whole thing in R3. Okay, so what do I get? Here I have dt of d alpha U epsilon times d alpha U epsilon. That's just ddt of d alpha U epsilon L2 squared over 2. I'm going to be wanting to sum this over all multi-indices alpha less than or equal to m. Okay? So I have this plus the integral of d alpha U epsilon. Since d alpha commutes with the Leray projector, and since the Leray projector of d alpha U epsilon is itself, I can forget the p when I take the L2 inner product, and I get d alpha U epsilon times d alpha of this product, j epsilon U epsilon dot grad j epsilon U epsilon equal, here is where why we needed these two j's. Okay, so I'm going to have nu d alpha U epsilon, j epsilon Laplacian j epsilon U epsilon. Okay. This j epsilon moves around. Okay, so I can put, sorry, this is going to be a d alpha of this. Okay, so this j epsilon moves around, so I can put this j epsilon right here. Okay, so this is the same thing as nu times, this is properties of convolutions, dotted with Laplacian of d alpha j epsilon U epsilon. Okay, all right. This Laplacian I can integrate by parts. Okay, so when I integrate by parts, I have minus the gradient of this guy squared. So this is negative, or non-positive. Okay? All right. So we're left with, do I want to throw this away already? Not sure, actually. I think I threw it away too fast. Okay, this is true, but okay. Now, I need to deal with this term. Sorry. This term. Okay? For this, I'm going to need what's called the calculus inequalities. Okay, so actually, I do want to throw this away. All right. Where am I? Okay, so I want to write this term here, d alpha U epsilon d alpha of this product as d alpha u epsilon times d alpha of the product minus grad j epsilon d alpha u epsilon. Okay. Plus d alpha u epsilon times dotted with j epsilon u epsilon dot grad j epsilon d alpha u epsilon. And this j epsilon here, I'm going to move it around. Okay? So first I'm going to write this. Okay? I could do that. The convolution commutes with the derivatives. All right. Now what is this? Okay. This is d alpha. This is some function. Let me call this f for a moment. Times j epsilon u epsilon, j epsilon grad, dotted with the same function f. Okay? It turns out that this is 0. Okay? Because this is the same thing as j epsilon u epsilon times j epsilon grad of f squared over 2. Okay? And the divergence of this thing is 0. Okay? So this term here is 0. I seem to be missing a j epsilon here.
Yes, there was a j epsilon.
Ah, yeah, there was another j epsilon that I somehow removed. Yeah, there was a j epsilon here. Here it doesn't make any difference, but here it does. Okay, sorry about that. There's supposed to be a j epsilon. Okay. So then, this is going to be j epsilon of this. All right. And let's see. Yeah. Okay, so this term, so I have, so I can move the j epsilons around. And I can put this j epsilon onto here. Yes, now it's okay. Okay, so I'm going to still have j epsilon here. And finally, I'm going to have this. Yes. Now it's okay. All right. I'll put this guy back here. Okay. All right. So now this is f, and now this is just this. Yes. J epsilon dot grad applied to f. And this is 0. Okay. So I'm left with my commutator. And this guy here is going to come onto here. I'm left with this commutator. All right. Now let me call this guy here v. Okay. J epsilon u is v. Sorry, grad of j epsilon u. Okay. So this thing here is the same thing as, I can rewrite this term as d alpha grad j epsilon u. Okay? So I have d alpha of j epsilon u epsilon dotted with v minus j epsilon u epsilon dotted with grad of v. Okay? Grad of d alpha v. Remember this. Now I need to use the calculus inequalities for the commutator. The commutator is always better than either part, either term. is it? Okay, I'm good. The sum for alpha less than or equal to m of d alpha u times v minus u d alpha v hm is bounded, sorry, L2, L2 is bounded by a constant times grad u L infinity dm minus 1 v L2 plus dmu L2 v L infinity. Okay. Of course, the sum over all alphas, all multi-indices up to m, is giving me the HM norm of this commutator, which is what I want. Okay? So I'm using commutator, this calculus inequality, this commutator estimate, with this guy here being u, this is being v, so this is d alpha of u times v, minus u times d alpha of v. Okay? All right. So using this, we get my nonlinear term, integral d alpha d epsilon dotted with, is it j epsilon d alpha and now it's the right thing, right? It's j epsilon, u epsilon, grad j epsilon. Okay. Okay. So if I sum this, over all alphas less than or equal to m, okay, then what do I get? I'm going to get constant times, first of all, d alpha u epsilon L2 from here, and then the sum of the L2 norm of my commutator. Okay, there's a j epsilon here too, but that doesn't matter because it goes away when you take the L2 norm. Okay? All right, so I'm going to get constant times gradient of u. So this is u. L infinity times dm minus 1 of v. So dm minus 1 of v, for emphasis, let me write it like this. This is L2 plus dm j epsilon u epsilon L2 times v L infinity. So here's v. There. Okay? This is bounded by grad u epsilon L infinity, okay, which in turn, because m is bigger than 3/2 plus 2, is bounded by the HM norm. So when I sum over all alphas, I'm going to get C, u epsilon HM here. Here I'm going to get another u epsilon HM, unless I'm mistaken. Just a sec. Am I forgetting somebody? Okay. This is right. Okay. And then this term here is actually an mth derivative of u epsilon and L2. So I have a hm squared from here. Okay. Plus again another mth derivative. So I again have it hm L2. Here. And another hm L2 from here. Because this is the L infinity norm of the gradient of u epsilon, okay? And then the gradient of u epsilon belongs to hm minus 1, but m was bigger than 3/2 plus 2, so m minus 1 is bigger than 3/2 plus 1, so it's still above the critical exponent, so this still belongs to L infinity. In other words, I can still estimate this by hm. So bottom line, I have hm cubed. Okay? And now I'm going to put everything together, what I've got. Okay. So, once I sum over all alpha, all multi-indices less than or equal to m, I'm going to get the hm norm squared of u epsilon is bounded by this term which I threw away plus constant times hm cubed. And there's no more epsilons here. Okay? Sorry. All right. Or if you want, in other words, canceling out the relevant factors, you get hm bounded by constant hm squared. So this is just twice u epsilon hm times ddt of u epsilon hm, so you cancel one on each side and you get this. Okay, so this gives you blow up, okay? Or at least this tells you that up until a certain time, you do not have blow up, okay, but there is the possibility of blow up, okay? All right, so u epsilon times t hm is going to be bounded by u naught hm over 1 minus ct u naught hm. When you integrate this, that's what you get. Okay? Integrate this up until time t, for little t less than or equal to capital T. Okay? So as long as this is positive, you're okay. All right? So this is okay if 1 minus ct u naught hm is positive, so t is less than, t is less than 1 over u naught hm. Okay. Of course, that doesn't tell you that you do blow up. It just tells you that you lose your estimate. Okay? All right. The nice thing about this is that this is independent of epsilon. This estimate is independent of epsilon. So it tells you that up until time, sorry, I missed something. Okay. I did the wrong estimate, apparently. So this is one thing that you get. The other thing that you get, all right, from the same thing, okay, is if I take this guy, this L infinity norm, okay, the term with the Laplacian, I just threw away. Okay, so the nonlinear term also have ddt of u epsilon hm squared less than or equal to a constant times grad u epsilon L infinity u epsilon hm squared. And what I did was I substituted this for u epsilon hm, and I got the u epsilon hm cubed. Okay, but I also have this estimate here. Okay, so what this estimate tells me is that u epsilon hm squared is less than or equal to whatever it was initially times the exponential of times the integral of this exponential. Sorry, the exponential of this integral. Starting to get a little. Okay. In particular, this tells you that you don't have blow-up for fixed epsilon, because as long as this is finite, this will be finite, and so you can prolong your OD, your existence, a little bit longer. Okay. And of course, this is less than or equal to this. So this tells you that for fixed epsilon, no blow-up. In fact, I could put a J epsilon here. Okay. Get this ahead of this. Because what really appeared here is the gradient of J epsilon, U epsilon and L infinity. And I threw away the J epsilon. Okay, so since I do have the J epsilon there, that's always smooth, and therefore that's always finite. Okay. All right, so for fixed epsilon, this blow up. This is always finite, and you can always prolong your solution a little bit further. Okay, so actually this is step 2 and probably step, yeah. So this was step 2 and 3. This is actually step 3. Okay, and this is step 2. So you have a solution for all time for fixed epsilon and with a uniform estimate in HM 3 up until a certain time. Okay. Now, let's look at dt u epsilon. Okay. So ddt of u epsilon is equal to all of this stuff. This guy minus this guy plus this guy, right? Minus p j epsilon u epsilon dot grad j epsilon u epsilon plus mu p j epsilon Laplacian j epsilon u epsilon. All right. We've already shown that this object here remains in HM for up until time t, capital T, and here what you're going, if u epsilon belongs to HM, the Laplacian of u epsilon will get you into HM minus 2. Okay. So if you have j epsilon minus 2, sorry, this is the gradient of j epsilon. This will belong to hm minus 1. So the bottom line is dt u epsilon belongs to L infinity hm minus 2. And this is locally up until time capital T. Okay. This is for t less than t less than t star. And then this guy here is my t star. Okay. Okay, so I have this, and I have u epsilon is bounded. Not only this belongs here, but it belongs to a bounded set here, bounded with respect to epsilon. So U epsilon is going to be bounded in L infinity in time Hm at x. And then there's something called the Abelian lemma, which there's various forms, and the form that I want to use now is this. If I have three Banach spaces x, y, and z, such that the embedding of x into y is compact, the embedding of y into z is continuous, and I have 0t into x, 0t into y, into z. I have a sequence of functions which is bounded from time into x. So it's L infinity in time into x, into the good space. And I have a stronger estimate in time into the weaker space. So I have equicontinuous into z. Then the Abelian lemma tells me that I'm going to be compact in C of 0t into y. Okay? So I want to use this with x equals to hm, z equals to hm minus 2, and y equals to hm minus 1. So my sequence is going to be compact in time into hm minus 1. And therefore, I can pass to a subsequence without relabeling, which converges finally into hm minus 1. Okay. Now notice that dtu will obey the same estimate as u epsilon, so it's going to be bounded into hm minus 2. And because of the choice of m minus 2 is greater than 3/2. So this is L infinity into C0 in x. Okay, so u is at least Lipschitz continuous into continuous function, Lipschitz continuous in time into the continuous functions in x. In addition, okay, u epsilon is going to be continuous into C1. Okay, so the final step, which is to pass to the limit here, okay, final step this was step 4. Final step, pass to the limit. I have dt u epsilon plus p j epsilon u epsilon of grad j epsilon u epsilon is nu p j epsilon Laplacian j epsilon u epsilon. And what I want to say is that, first of all, this can be rewritten as a divergence of this tensor product. In particular, this object here will converge strongly because you have strong convergence in HM minus 1. In particular, you have strong convergence in L2. This will converge strongly to U tensor U. Okay, the J epsilon will go away also. So this term here converges to P times divergence of U tensor U. Okay, strongly in L2. This guy here is converging to this by linearity, and this will converge again to this. Okay, at this point I'm fudging a little bit. Okay, this is a little bit more delicate than what it looks like. Okay, there's some more detail here, but the main ideas are already here. Yes. I can't hear you.
The convergence is just locally in space, right?
I'm sorry?
The convergence is local in space.
The convergence is local with respect to x? No.
In space. Is it local or global in space?
I cannot. Can you speak up, please? I'm okay.
I'm talking about.
I'm going deaf.
It's just about the convergence. Is it locally or globally in space?
Oh, it's global in space. This is global. Oh, I'm sorry. No. This is local. You're right. This is local in space. Like I said, at this point, I'm fudging. Okay? There are some details that are missing in this step. Okay? But I wanted to give you, the main ideas. Okay? At this point here, okay, so some details missing. Okay. All right. Another thing which is a very important detail that is missing here is how do we deal with time? So one detail, you're right, is the compactness has to be local in space because this compactness, HM minus 1, where am I? Where's HM minus 1? This compactness here is only local in space. Okay. All right. But another important detail that's missing is how time behaves. Okay, this dt u epsilon converted to dtu. It's a little bit iffy, okay? And so you need to work, that's a little delicate. You need to work that out separately, okay? Okay, and again, and this is actually the place where you distinguish between Euler and Navier-Stokes. So up until here, the proof for Euler and for Navier-Stokes is exactly the same. In other words, nu greater or equal to 0, okay? And this is the place where you have to distinguish because Euler is time reversible and Navier-Stokes is not. Right, so this is where things get a little weird. Okay.
You always consider the dimension 3, but dimension 2.
Yeah, I'm considering always dimension 3 because I put m minus 2 greater than 5, so I could put n minus 2 greater than n over 2, in particular 1 in dimension 2. Okay.
Your proof works.
Yeah, it works in any dimension. It's not mine, but yes, the proof works in any dimension. That's correct. I'm stressing R3 because it's where things are a little more complicated. Okay? It's already noon? All right. So I was going to do Beale-Kato-Majda, but that will have to wait until the afternoon. Thank you.